Let's get started with some admin. I'm just going to redo this stuff. So first of all, assignment 2, don't forget academic integrity, it's paramount. Don't forget to make sure you understand ownership. I just want to reiterate what I said a few moments ago. With group work, we are not about counting who wrote what line of code. We're about you as a group feeling like the group worked well together and that you distributed the load well and people did what they were expected, okay? So it does not mean that you each wrote every third line of code or you each wrote so many tasks and this many tasks. That's absolutely not the way a group should be working. A group should be saying, okay, I'm going to do this part and I promise, and you know, this is what I'm going to deliver by this date and so forth. And you know, some of you will have strengths in the graphics, some of you have strengths in debugging, some of you have strengths in creativity and so forth. You're all going to have different strengths and weaknesses. What we want to see is a group delivering a great outcome with your different strengths and weaknesses compensating for each other. Okay, that's what we care about. And so we want you to think of it that way. And that is actually, despite what some of you have learned, that's actually how things work in industry, is that we have teams have very diverse strengths and weaknesses, and you want to bring them together to maximize the best outcome. Okay. The next deadline is, I think it's on Friday, but the D2E is the next deadline. And one thing that's important for that deadline is that it asks you to generate a jar file. It tells you how to do that. But the point about the jar file is that's part of your final deliverable because you're going to ship the thing as a jar file. And we make it as a D2E deliverable, which doesn't have very many marks associated with it. But this gets you used to packaging a jar file, which can be a bit fiddly. So we want you to do that early, okay? Learning how to create a...
Oh, sorry, Steve. I think Stanley just asked a question. Is it meant to be Monday week 8 admin slides? So because it says admin Monday week 8.
Oh, okay. Yeah, today's Friday, folks. It's not Monday. Don't worry too much about the text at the top of the slide. That's pretty obviously a typo, okay? Hopefully people can realize that today's Friday. Like it says on this slide here. So folks, when you see typos like that, if you think it's really helpful to highlight them, then please do. But in a case like that, where it says Monday and everyone knows it's today's Friday, don't stress too much, okay? And this is the admin for Friday. Labs, next week, you're going to do some search. And in the next 3 weeks, one of the things you should be doing at each lab is talking to your tutor and going through and asking your tutor for help with the assignment and raising issues with your tutor. Make the most of that opportunity to discuss your assignment with your tutor, okay? Now, I wanted to highlight this. This should be fun. This is something that's happening next Tuesday. I just posted this on Piazza, okay? And what this is on is a chat with 2 ANU alums, Suvash and she is a former PhD student of mine. He did a bunch of work with me and he's they're both fantastic guys, but she I know really well because we worked together for 5 or 7 years, I think, in all. And I'm still working with him now. And they're both at Twitter. They both have really interesting jobs at Twitter. And this is an opportunity for 1 hour to hear them talk about their time at ANU, their time at Twitter, other things they've done, startups, like she was in a really interesting startup for a while, and all sorts of stuff like that. And you can ask them questions. That's the really cool thing. It's going to be on Zoom. You can type in questions. This particular one, I'm going to be hosting. So there's a series of these things, and this one I'm hosting. Anyway, these are open to everyone. So they're aimed at everyone from first-year undergrads to PhD students through to academics. Everyone's invited to go to these things. So I just want to plug this thing and encourage you to come along if you've got time. All right, so I think you'll find this really enjoyable if you do have time. And I think they're going to be recorded, so maybe if you miss it, you can catch the recording later. All right, let's move on. Right, so now we're going to talk about exceptions. This is the next topic and one of the very last topics in our Java series, and it's a more advanced topic. Before I start talking about exceptions, I want you to all think again about how control flow works, okay? I want you to think about control flow and what you learned about control flow at the beginning of semester and what you learned since. And maybe you can put in the chat, what are the things you've learned about control flow? There were 3 things that I started the semester with. Then there's another thing I added around week 5 or week 6. And today we're going to add one more thing to our understanding of control flow. So if you can think, what were the 3 things, the 3 elements of control flow that we learned, I think, in week 1 of semester? Sequence, right? Selection and iteration. They're the 3 key ideas. And I illustrated this with a Jacquard loom and so forth. So sequence says in an imperative language, you do the one line after another. Selection says sometimes you can have branches. So you say, if this, then do that stuff. Otherwise, do that stuff. That's selection. And iteration says we have a construct that allows us to loop. And if you combine those together and add methods, then you have a very rich programming language. Okay? And that's key ideas in control flow. What's the other thing that I introduced you to? Can anyone remember the other key control flow thing, which is a very strange one that I introduced to you late, I think week 5 or week 6? Anyone know what that is? If you know what that is, just put it in the chat. Events, right? It was events. Yeah?
Joshua's just lambdas and events.
Yeah, lambdas aren't the control flow. That's a great suggestion, Joshua. So, but lambdas, to be clear, lambdas are the mechanism we use to do the control flow, but the control flow itself is the event. So yeah, that's exactly right. It's events, and we use lambdas to say what's going to happen in that event. Now, if you remember back, the idea of the event was when someone hit a key on the keyboard, you suddenly wanted to break out of that sequence or selection and jump over there and do the thing to handle the fact that someone pressed the key. Right? So they're breaking our normal model of control flow. That's what events are doing. Okay, so they're breaking out from this idea of sequence and selection and iteration, and suddenly you find yourself transported to something that handles that event. And how do we do that? Well, we tell the underlying system, hey, when you get a key press or when you get a mouse click, do this thing. And the lambda, as Joshua said, is the way we describe the thing we want done when that happens. Okay, well, exceptions are another flavor of control flow that actually a little similar to events. In the similarity is that you jump to another piece of code. Okay, so you jump from one thing to another thing according to some exceptional event, as the name indicates. Something exceptional happened. Okay, so why might you want to do this? Can anyone think about why we might want to do such a thing? And we're thinking about exceptional events. Can anyone imagine? Any suggestions on the chat there, Leah? Why would we want to have a mechanism for handling exceptional events? I'm just going to drink my coffee here.
Yeah, we got one from Evan. He said if an error occurs.
Absolutely. If an error occurs is a great one. So the thing that's interesting about errors is you want to have a systematic way of handling errors or strange things that happen. And there are lots of things that can happen. You can make a mistake in your program. That's bad, right? And it's hard to deal with that. But more often what can happen is your program can make assumptions about the outside world, like where a file is or what's in here or what input you're going to get from the console. Those things are assumptions about the outside world. You can't really control those things necessarily. You can say, well, we hope there's a file there, or expect this network connection to be open, or whatever. But those things those assumptions could fail for reasons that are outside your control. Okay, and in that case, you need to be able to deal with that. Okay. And often you want to do that in a centralized way or in a systematic way. You don't want to have to write all the way through error checking code that handles all these things. Okay, so exceptions are a very carefully designed thing that many programming languages have to deal with this idea of something exceptional happening. Now, before I flick to the next slide, I wonder if you can put in the chat any ideas that you might have of exceptions that you can think of in Java or maybe any other language. What's the idea of an exception? Can anyone think of exceptions? I gave you some hints just a moment ago in my description. Can anyone think of examples? Now I've listed.
Yeah, we got a few bad input, null pointer exception.
Yep, null pointer exception.
Null reference exception. Auto bound, index auto bound, array auto bound. That's a lot.
Great. You guys are right onto it, and you can see I've listed a bunch of the things you just said on the bottom of this slide here. Okay, so things that happen in exceptional situations. And notice that some of these ones, like a division by 0, is probably caused by a bad piece of code. That is, the person who was programming it wrote the code, didn't think carefully when they wrote the code. Likewise, if you access an array out of bounds, that's probably because you didn't write the code carefully, and the same with a null pointer. But a file not found, that may have that may arise even though the code was written carefully because something changed outside of the program, like someone deleted something that they shouldn't have deleted. Okay, so, and this is an important distinction because Java makes a distinction between these different kinds of things. Okay, and we're going to talk about that in a moment. But the key idea is that when these exceptions happen, we disrupt the normal flow of execution. So instead of doing this sequence and selection and iteration, we're going to jump somewhere else and handle the exception. And the way it's handled is through what we call an exception handler. And in this class, first of all, in this part of the lecture, I'm just first of all telling you the concept of an exception, which many languages have. And that's what I've just done now. And then we're going to move on to talk about it concretely, how Java deals with exceptions and the particularities of Java's exception handling. So now, Java exceptions. Javas are thrown either implicitly, so that's when there's an error in the program, or explicitly. Now, why would we ever want to deliberately create an exception? So implicitly means the program spontaneously throws an exception, right? Explicitly means that we, the programmer, say, hey, I want to throw an exception now. Can anyone think, and maybe put it in the chat, why would you ever want to explicitly throw an exception? Try and think of it. And I'll give you a little clue in case you're scratching your head. I'm going to run through an example soon, and I hinted at it in Monday's lecture. Okay? There's a hint in Monday's lecture, and we're going to code it up soon in a few minutes. Now, the next point is that when an exception happens, there needs to be a catch block that catches the exception. And the way it works is that you've seen a call stack, like on the Waterloo visualizer. And what happens is, in the method where the exception happens, if there's a catch block in that, we're going to see catch blocks in a moment, but if there's a catch block inside that method, then that will deal with it. If there's not, then this method will propagate it to its caller, and so forth, all the way. If no one catches it, ultimately it'll come to the main method. And if the main method doesn't catch it, your program fails, and you'll get an exception on the command line, which you've probably all seen. You've probably all seen null pointer exceptions or other exceptions like that. That's what happens if the exception isn't caught. Okay. Now let's have a look. Do you hear anything, Leo? Any responses to my question about why anyone would want to explicitly do an exception?
Oh yeah, I think Georgia said we probably want to test our code with that.
That's a great example for testing, but you may want to write defensively. Now, one example we're going to see in a few minutes is that we went and implemented a list. If you remember right, on Monday's lecture, we implemented a list. And when I wrote that, some of you said, hey, we need to check to see if someone gave us the wrong index into the list. Like the list only had 3 elements and someone said, get element number 4. What should happen if that happens? Well, it should be an index out of bounds exception, right? That's what should happen. So where does that come from? Well, in that case, if you're the person implementing the list, which is us, which is what we're going to do in a few minutes, then we need to explicitly throw that exception. So we say, hey, you've asked for element 4. There's only 3 elements in this list, so I'm going to throw an exception. Okay? And that's an example of where you throw an exception, because the user of your piece of code is doing the wrong thing, and you want to throw an exception to reflect that. Okay? So that's an example of where we'll do it explicitly. You're going to see that in a few minutes. So here is a special rule in the Java language, and it's the catch or specify requirement. And it talks in terms of 3 kinds of exceptions. The first kind are error, and that is a class called error and has a number of subclasses. This is unusual. You don't normally need to think about this. This is things like where the actual Java crashes or something weird like that, which is really beyond your control. Okay, so that's when something really bad happens that it really has nothing much to do with your program, but the system behaves badly for some reason. That's an error. Okay, so generally you don't have to worry about those. Runtime exceptions are really common. And runtime exceptions are when you do something bad in your program that is within your control as a programmer, but it is not a function of the outside world, right? So, and those ones are things like divide by 0, null pointer exception. These are things that reflect on your code, okay? And you probably can't handle that. There's often not much you can do about that. If someone does a null pointer exception or a divide by 0 exception, there's not much you can do about that except fix the code, because the code's wrong, okay? On the other hand, and those things are what we call unchecked exceptions. So errors and runtime exceptions are what we call in Java unchecked, okay? And the reason why they're unchecked is because really this stuff shouldn't have happened, and stuff's really gone wrong, and there's not a whole lot we can do about it, okay? Probably, okay? So you can catch those and you can deal with them, but you're not expected to, because these things are not supposed to happen. You're not supposed to have null pointer exceptions. You're not supposed to have divide by 0 errors. On the other hand, there is another class of error called a checked exception. And this is everything other than the ones I just listed. And this is things like a file not found exception. And these ones are things that you can handle, okay, in principle, and you're expected to handle by Java, okay? So if you go and try and access a file, you're expected by Java to say, okay, if the file's not there, then do the following, right? And that's why it says whenever you do a file IO operation, you've got to catch the possible exceptions that might happen. So if the operating system says, oh, that file is locked, or that file is read-only, or that file doesn't even exist, any of those sort of things, then you get thrown an exception, and you as a programmer are expected to deal with that, okay? Because you're writing code, and you should know that the outside world can have these issues, so you're expected to write a handler for it. And in IntelliJ, luckily, it already prompts you for this. So whenever you do something that requires a try-catch block, it'll prompt you to do that. Okay, and likewise the compiler will when you run your code. If you're not using an IDE, it'll say, hey, you need to put a try and a catch here. Okay, so let's reiterate. There are unchecked exceptions, which include errors where the whole thing just goes bad. Runtime exceptions like null pointer exception or divide by zero exception, where they shouldn't happen, and so if they do happen, then things will really run amok. And then there are checked exceptions, and checked exceptions are ones that you should be able to anticipate because they're ones we all understand might happen, like a file not being there. And for the latter, the checked exceptions, you need to be able to catch them, okay? And there's two ways you can do that. You can write a try and a catch, or the method that's doing the thing can throw the exception, which means that it's basically delegating the problem to whatever called it, okay? So the way we've typically done it in class and the way we're mostly going to do it is writing a try and a catch, but in other situations you might want to just say, okay, this method could throw an exception, and you write throws in the method declaration. All right, so what does a try-catch look like? This is interesting. So this is the code we use to in Java when we're writing something that might generate an exception. We say try, and then inside the try block we have the code that we're, like, for example, opening the file, right? And then we can have multiple catch blocks. Often we just have one. And you'll notice the second one here, this says exception E2. That's a general purpose one. It doesn't say what kind of exception. It's just the superclass of all exceptions. And it'll catch any exception at all and do whatever code is in here if that exception, any kind of exception arises. But in front of it, we've got more specific ones. We've got, like, for example, here we've written arithmetic exception. It could be some other exception, but this is a specific one, okay? And what Java will do is, if an exception happens in here, it will first go to this catch and see if it matches that one. If it doesn't, then it will go to that one. So if you had a null pointer exception, for example, because you accessed something here that was null, then it would come here and say, oh no, it's not an arithmetic exception, and it'll go here and say, oh well, it is an exception because null pointer exception is a kind of exception, and it will do whatever you wrote in this piece of code right here. Okay? And then you've got this thing called finally, and this is a place where you can write code that will always happen regardless of what happens here. Even if this thing succeeds, it'll always do this code. This is interesting. So it means that if this thing succeeds or it doesn't succeed, it will always end up coming here afterwards. So if something bad happens here, you get an arithmetic exception, it'll still do this block of code. Now, interesting question. Why would you ever want to have a finally block? Can anyone think of what might motivate having this thing here, which always gets run? And I've given you a hint there with my comment there on the last line. Can anyone think of an example? Did you get anything there, Leo?
No, I think there is slight delay.
Okay, yeah, too much of a delay. Well, I'll give it to you anyway, folks. An example is, for example, if you open a file, then you try and do something with it, then you get an exception, you want to close the file before you continue on. So there are things like that which are essentially cleaning up jobs that you might want to do. So if there are things you need to clean up when stuff goes wrong, you put them in the finally block, and that way they get cleaned up whether or not stuff worked out, okay? That's what that's for. So now let's go to the mini quiz and publish the poll. There we go. And now we're going to write some code. Okay, and where we're going to write it, we're going to write it here in J15. And let me see my notes here. Okay. We're going to write ourselves a little class here. New Java class, we're going to call it exceptions. Oops. And yep, add it to Git and write ourselves a main method. And There's our main method. And what we're going to do is write just some really simple boilerplate here, like this. One of the things that people find mysterious is how the control flow works. So I'm going to write some code here, which is really simple and kind of stating the obvious. But I'm writing it here so you can watch how the control flow works by watching the program get printed out. You could also use the visualizer or something like that to watch the control flow. But here, I'm just going to write this code here so you can see what's going on. And then what we're going to do is write another method up here. Some random method here. You could call it whatever you want, but I've called it exceptional method. Okay, and then what we're going to do here is same sort of stuff, just so you can see what's going on here. I'll just write method like that, and in here we'll make a call to that. Okay, so exceptional method. I didn't spell it right, did I? Okay, all right, so now let's run this, and it's going to do the obvious thing here, and just print out a bunch of lines of messages. Not very exciting. But what we're going to do in a moment is we're going to put some exception generating code up here so you can see what happens to the control flow. Because remember, the whole point about exceptions is we're going to change the way control flow works, okay? So so now you can see the obvious. It starts the main method, then it jumps into the method, then it ends the method, and then it jumps to the end of the main method. So this should be obvious enough to you and unsurprising, right? So now what we're going to do is, first of all, we're going to, we're just going to create an object here. There's nothing magic about this, but it's just a useful example. Date, like that, just a standard date, Java standard date thing. We'll say date equals new date. Like that, okay? And then we can just say s out, and then just print the date. D.toString, like that. Okay, so we run this now, and it should be completely unsurprising. Should print just the same as before, but now should print out the date when it's in the method, right? Between the start and the end of the method, it'll print out the date. Okay, very unsurprising. Now what we're gonna do is something more interesting. We'll say this. So now what you should expect to see is that when it goes to print this out, right, it'll say, hey, wait a minute, you're calling the toString method on a null? You can't do that, right? It should throw an exception. So let's watch what happens now. Okay, and what's going to happen on the screen here should, this is probably what you've seen before. This red text at the bottom of your screen, and what's going on? It says there's an exception in the main thread. And it happened in line 10 and line 15. So line 10 is where it is here, and then it fell down here to line 15, and then the program ended, okay? Notice, look at this. It says start of main method, start of method. This other text didn't get printed. It did not print this line of code out. It did not print this line of code out. It exited the program at this point here, okay? So this is very important to understand, right? So because the exception handling has not, all right, so the exception we don't have any exception handling here. We're not handling the exception at all. Okay. Notice we don't need to handle exception either. So IntelliJ is not saying, hey, you need to handle this exception, because it's not a checked exception. Okay. Null point exceptions and divide by zero exceptions, you don't need to handle them. Okay. The sort that you do are the ones like file IO, which I mentioned earlier. So now let's do something else. We'll just do let's just write a try catch around it. Let's try and do this stuff here. Write a catch here, and then what we're going to do here is going to just catch an exception E, and we'll say a generic exception, something like that. Okay, and so what we expect to have happen now is that when we get to this point, when this bad thing happens, it should jump straight to this exception handler and print out this, okay? And then what do you think is going to happen after that? Okay, I want you to think about what's going to happen next, okay? We've handled the exception because we've got a catch clause here now, which will catch that exception. look what happens here, okay? So you see start of the main method, start of the method, then bad stuff happened, but we caught the exception. We print out that message saying the exception was caught. You can see that down there. And then the method got to its end. So then we jumped from that line down to here, and then we got down to the main method, okay? And exited the main method gracefully. So now there's no red stuff everywhere. The same bad thing happened, but we handled it, okay? So we've handled it by catching the exception with a catch clause. Okay, so now let's make things slightly more interesting. What happens if we do the following? Can anyone guess what's going to happen here? Actually, no, let's not do that. Let's do this. What's going to happen here? Can anyone guess what's going to happen when the code's like this? I want folks to, can anyone say what's going to happen when...
Yep. Joshua said the same result, and Adam explained that by it will catch it as well.
Well, those two things are different, right? It would catch it, but the point is, what's really interesting here, it does give you the same result. That's correct, right? But the reason why it gives it the same result is because the exception happens here. So this code never gets executed, okay? This code never gets executed. Right, so we can check that by saying let's run it now just to make my point a bit more clear. Okay, this code never even happens. It never gets executed. That's because the error happens here, and it jumps straight down to this exception handler. Okay, so this doesn't happen, and so of course this doesn't happen either. But if we do this, well, actually, let's do one more thing. Let's change this to a null pointer exception. Okay, so oops. If I change this thing here to handle a null pointer exception, then we run this, we should see a message here saying a null pointer exception was caught, right? Because at this point here on line 11, yeah, null pointer exception was caught, right? Now what happens if I move this guy to the top here? What do you think is going to happen now? Can anyone guess what's going to happen now? So what's going to happen? Yeah, go ahead.
Josh just said this will fail.
That will fail, exactly. And look how it fails. A divide by zero exception, right? It's a divide by zero exception. So we've got a divide by zero exception because we're not catching it, okay? Because what we're catching is quite specific. We're catching a null pointer exception, which is what this one was, but we're not catching a divide by zero exception. So what I could do here is this. Oops, that's not what I want. No, don't do that. Right, so I can make it non-specific like that and get rid of this horrible thing I didn't mean to include. Okay, we run it now. Now what should happen is when we have that divide by zero, it should jump down to this one and be handled gracefully. Okay? And there we see it. Generic exception was caught. All right? So hopefully this is making sense. The last thing I'm going to do is put a finally clause in here. And we'll say finally, and we go like this. And we'll note what should happen now is we should get a generic exception, and then the final part gets executed as well. Notice if we get rid of this bad thing and get rid of this bad thing, now what should happen is this should work, and the finally should also work. Let's have a look. Right, so now look here, we see the start of the method, we see the date does get printed out, so this line is working now. Then this line does actually happen. And then notice it jumps now to the finally. So it jumps down to here because the finally always happens whether or not there's an error. So let's put this bad code back again, like that, and we'll see the finally code is also happening whether or not there's an exception. Okay, so finally still happens when there was an exception, null pointer exception caught. Okay, with that we finished that piece, but what we're going to do now is something else important which I hinted at in our last class, and that is we're going to add exception handling to our, we're going to do two things here. Our lists should throw exceptions. When someone tries to grab an element that's outside of the range of the list, we should throw an exception and say, hey, you've tried to access something that was outside of the range of this list. So that's one thing we should do. The other thing we should do is we should test for that. So we're going to do that right now. Okay, so I'm going to cut and paste that code, the code that we wrote in Monday's lecture. We're going to cut and paste it here. And what's happened here? Why have we got red stuff? Oh, they're all happy. Okay, all right, good. So now let's remember the interface? We wrote this code the other day. So which ones of these should be throwing exceptions? We want to throw exceptions now. So before we're catching them, and they were implicitly generated exceptions. They were exceptions that happened because we wrote bad code, such as the null pointer exception, such as the divide by zero, which you can't do. Now we're going to actually explicitly throw, rather than implicitly throw an exception, we're going to explicitly throw an exception. Which ones of these do we want to have explicit throwing on? Does anyone know? It's actually just this one and this one that we really want to throw an exception on, because if that index is bad, then we've got problems. Okay, so, and some of you already mentioned this when we wrote the tests here, that we wanted to do some of these things. Okay, so check the length and so forth. Okay, so now let's write ourselves some tests that actually check whether the exceptions are being thrown. And so let's do the following. We'll say at test. The way we test for exceptions in JUnit is this. We say expected, and then we can say that it equals, and we can say index out of bounds exception. That's what we want to get. We want to get an index out of bounds exception when someone goes off the end of a list, just like if they go off the end of an array, right? So we say index, there it is, okay? And I just need to include that. Come on. What's happened here? Oh, yeah, it's going to be the class. I've got to say dot class. Okay, so the expected is going to be the class. Oh, what's the matter now? What have I done here? Public. Oh dear, I think what's happened here is that I have not updated my notes for JUnit 5. And with JUnit 5, that's how you specify it. I'm gonna have to look this up unless someone beats me to it. Let me just write this test first as if I was right. Empty. So what we want to do here is, just like this, we'll say, create ourselves a list. And then we want to access, say, the 0th element, l.get. Does anyone have notice how to do this in JUnit 5? I've just messed this up. This is how you do it in JUnit 4, exactly like that. But I've done this wrong. Here we go. See if this gives me a hint. Nope. 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 Okay, I've screwed up.
Hey Steve,
yep.
I just checked the JUnit 5 document, and the example it gives me is you need to use assert throws method rather than using the expected exception class. So in here, I just say assert throws? No, I think I can just, yeah, and then also put the... sorry, folks. We just made the transition to JUnit 5, and I've messed up here. So I'm gonna. Can you take a look at the chat? Because Michael just sent you the code snipped. No, I don't have that chat open. I've got the other chat open. So if you could just post it in your chat. Sorry, it's a little bit chaotic here, folks, because I've got multiple things going here when I run the lecture, and I do not have your chat there. But Leo's posting it to me. So sorry, folks. I just send it to you. Yep.
But so there's some syntax here which I've gotten wrong because this is JUnit 4 syntax. We need JUnit 5 syntax. But the important point is we've written some code here, and what's going on is we're accessing an element from something which has nothing in it. Okay, we've created there, it's empty, and now we're accessing an element from there, and that is that should throw an exception. Okay, there we go.
Yeah, that's a syntax Michael used for his assignment. So you can see that you need to use the exception class and use the method as a throws.
Oh, okay. This is dang. All right. That's not what we want for here. That's not how we want to do it here. Let me. Sorry, guys. I'm really apologize for this. So I'll just look for it here. JUnit 5.
Yeah, I can also send you the link as an post in the chat.
All right. Sorry, folks. Yeah. Okay. Oh, I see. Right. I see. All right. Thank you for that. So we don't need this annotation in JUnit 5. You just do this. Okay. And then what we do instead is this code here is the code that we expect to throw an exception. Okay. So what we're going to do instead is we're going to say the following. We're going to say assertions dot assert throws. There it is. Okay, and now what we're going to do is we're going to the type we want is an index out of bounds exceptions. There it is. Dot class. That's the exception we're expecting to see. Okay, and now we need to write a lambda which has the code that's going to be bad, right? This is just the way that JUnit 5 does it. Okay, and so what we're going to write in here is that. Okay, so that code there should throw that exception. All right, everyone follow that? So I wrote it differently before, but now we've got it written in the JUnit 5 style. So we say we've got a test here saying test that when the array is empty, we want to throw an exception. And what we should find now, of course, this test should fail because we're doing test-driven development and we've not written the code yet that does this. But let's just test it. And right, and it failed, which is what we expect. Unexpected exception type thrown. And in what we got here, but we got a null pointer exception. Our code died, but not the right way. It died with a null pointer exception, but what we should be doing is throwing an index out of bounds exception. So this is exactly what we want. So thank you to Michael and Adnan for that fix there, that hot fix in our class. I apologize for making that mistake. I should have worked through this code with JUnit 5 before the class. I just didn't think of I didn't realize I changed the syntax like that. All right, so now what other ones can we do here? We have to do it for get and remove. So that the one we just wrote was for get. Now we can do the same with remove, right? Because remove has the same issue, that if you try and remove something from an empty list, we're going to run into the same issue. And then we can repeat this for a few other things. What are they going to be? We want to not just do empty. So that's when so the examples we've got here is when our list has nothing in it, right? So we create the list here, and then we immediately start accessing stuff that isn't there. So those are when we're accessing something that's empty. We also want to access something that is not empty, but that is out of bounds, right? So we want to say ones that go beyond and ones that go run short. So we'll say overflow and underflow, okay? So we'll test get overflow. Get overflow. So so now what we're going to do is we're going to say l dot add. We'll add something. Right. So now it's not empty, but we're going to do something like get element 1 or just element 12. It doesn't really matter, but something beyond 0. Element 0 is in there now. That will be A. But element 2 won't exist, so we should get an exception. All right. So now we want to do the same thing with remove. That's get. Now we want to test remove to make sure remove behaves correctly. and then we're going to do underflow in a second. Okay. Oops. Sorry, typos here. Then we're going to do a remove, and now we're going to do the same thing again with underflow. Just cut and paste this stuff here, and we'll do underflow. That's over, and we're going to do under. Under means we're going to try and index below 0, right? So now we've tested for each one of these things. There it is, underflow, and we'll access element number -1 or whatever, or -2, doesn't really matter, anything that's below 1, right? Okay, so they're underflow, so it's accessing below what's reasonable. These ones are accessing above what's reasonable, and these are accessing things when there's nothing at all, okay? Now we can run all of our tests, and those ones should all fail, right? Let's hope they do. If they don't fail, that means that there's something wrong with our tests, because those tests, I mean, obviously the other tests should pass. So let's just check. We should have 6 failing, right? Yep. So there's 6 failing, which is exactly what we expect. Now what we're going to do is go and write the things to actually throw those. And we're doing the linked list first because it says array is false. So let's go to the linked list. And what we're going to do here is go to get, and we'll say, where is it? So remove, we can do remove first if we want. We say if index is less than 0 or index is greater than what? The number of elements, right? Greater than or equal to the number of elements. Then throw index out of bounds exception. Okay? We're going to throw that exception, and we need to include the import that method. Oops, no. Oh, you've got to create it. Sorry, you have to create. It's actually an object, right? So index out of bounds exception is actually an object. So we have to create a new one. So we say throw a new index out of bounds exception, and there it is. And we're going to do the same thing here for get. Okay, so let's just do that. Notice that code I wrote checks both for underflow and for, oh, hang on, I pasted it in the wrong place. We've got to paste it in here. Okay, so it checks for underflow and overflow, and this will also check for the case where there is nothing in there, because if there's nothing in there, this will be 0. Okay, so let's run our test again. This time, hopefully, everything will pass. Perfect. Okay, now let's go make the same changes to the array list. Oh, let's just first test that array list fails, which should do, right? Change that to true, run the test again. Now we should see 6 failures, right? For the 6 things we just added should all fail. There it is. Oh, only 2 of them failed. Ah, that's interesting. Why did 2 of them not fail? So underflow, oh, I know why they didn't fail. Can anyone guess why they didn't fail? The reason why they didn't fail is because their underlying implementation has an array in it. So what's going to happen is that if we access below 0, then we will access our array, which means that we will access element -1 of the array, which generates a index out of bounds exception. But one thing that this doesn't do, which is interesting, notice that if we change this, I bet this will change it, right? If we change this overflow to 1, then we might find, this is more interesting, because remember when we created the array, we created it with 2 elements in it, I think. This one here won't cause the array to overflow, but it's still out of bounds. Yeah, it's still out of bounds. So let's just check this and see if that changes. Get overflow. All right, get overflow. Where are we? Did get overflow change? No, it didn't. Let's go to the actual implementation, and if we make the initial size, oh, okay, the initial size was 1. Let's change this to 2. Or just change it, yeah, let's just change this to 2. Now what we should find is that it's not working, because what's going on is that we're accessing something within the array, but not something within the list. Okay, so we should, yes, and now we get 4 failures rather than 2, because the underlying array is no longer throwing the exception. Okay, so now what we're going to do is actually throw the exception explicitly rather than having Java do it for us. So we go in here and we'll say remove and put the exact same conditions here. We want to throw an exception if the index is less than 0 or if it's greater than or equal to the number of elements. And we'll do the same thing for get, wherever get is. Where's get? There it is. Okay. And we'll do the same thing for get. There it is. And now we run our test. and we should find that it passes. Now we're nearly out of time. I've run slightly over, but I really want to get on to the next module, so we're going to launch into that. We may run a little bit past the hour. I know I was a bit slow to start for a bunch of technical reasons. Hopefully you all understood that. You feel free to follow up with questions on Piazza if you still had that wasn't clear. But now you've seen me give two completely different examples of exceptions. The first one was catching implicitly thrown ones, and the second one was explicitly throwing them for our underlying list data structure. All right, what I want to talk about now is hash functions. This is a really cool topic. I think it's a really cool topic. And traditionally, for reasons that I find interesting / confusing, some people find this really hard, but I don't think you should find this hard. I think it's actually a really, if you think about it the right way, this is actually not a hard concept at all. What I want you to do, what I want everyone in the class to do for a moment, is think for the moment about me organizing a tournament. Okay, imagine we're back at ANU, we're on campus, we're going to do a tournament in the class, right, during the lecture. We're going to do a tournament, okay? And the tournament's going to involve two teams, Team A and Team B. Okay? What I want you all to do is think about a way for me to decide who goes into what team. And it's supposed to be just essentially random, okay? But there's some twists. There's some twists. Whatever your way of doing it is, needs to be systematic. Okay? It means that for any given student, like, you know, we see the student and we go, okay, you're an A. See another student, so like, oh, okay, you're in B. Okay? We've got a function. We've got some function that tells us for any given student whether they're in Team A or in Team B. Okay? You following me? Now there's one more twist. Okay, two more twists. One is I want A and B to be roughly the same size. They don't need to be exactly the same size, but roughly the same size. Okay, so I want roughly half the class to go in Team A, roughly half the class to go in Team B. Final twist, if we run it again next week, I want every person who was in Team A last week is going to be in the same team. That is, it's a deterministic function. Okay, if we apply the same function a week later, we get exactly the same outcome. Okay, so when I see a person walk through the door, I apply this function and I say, you're in Team A. If they walk through the door next week, I apply this function, they're guaranteed to also be in the same team that I said last week. How do I solve that problem? Anyone got any suggestions? If you've got any suggestions, please let Leo know. I'm really interested to hear what your thoughts are on this, okay? And this might seem strange. I mean, some of you, you're like, okay, so here's a solution which isn't going to work, right? If you did PE at school, you probably had times when the teacher said A, B, and just numbered people off, right? That's not going to work. Why isn't it going to work? Well, it's going to give two groups, yes. It's going to give two groups of roughly the same size, yes. But if I did that one week and then the next week, it'll give different groups because it'll just depend on what order you walked in the door, right? If you walked in a different order, then you might be in A or might be in B. It just depends on where you were sitting, right? So that isn't going to satisfy my requirements. My requirements say that next week, that same function for a given student is going to put them in the exact same team. Leo, did you get any suggestions there?
Yeah, I guess so someone's suggesting we should use the random class and give the seed. And Liam also said that we should order them by their UIDs, and then first half is A and the second half is B.
Yeah, okay, so we've got two suggestions there. I don't know if everyone heard that from Leo. Two suggestions. One was we're going to do it using random, but we're going to seed it. So random gives us the same thing every time. So it's basically like tossing a coin. So every time a student comes, we toss a coin, and we do exactly the same coin tosses next week as well. The problem with that, there's only one problem with that, and that is that next week the students might arrive in a different order. So even if the coin tosses are deterministic, the student arrival isn't deterministic. Okay, so if we could order the students and make the students come in the same order, then that would do the job. Okay, so it would work if you could order the students. And then the second suggestion was we get all the students and we get everyone to sort themselves by UID, and people go on the left if they have a UID that's high, and on the right if they've got one that's low, or actually put them in a long line and split the line in half. The problem is sorting everyone's UID. Man, that would take a long time. If we have 400 students, I can just imagine if I said to you, oh, hey, go sort yourselves out into your UID order, you'd be there for half an hour, I reckon. So I'm not sure that's going to work. Can anyone think of another solution that will work just like that? There is another way that will just work basically instantly that solves all these problems. Has anyone got a suggestion? And Liam was on the right track there, but getting everyone to be sorted, nah, not such a great idea because it'll take a while. Can anyone think of another way of doing it? Okay, I'm going to give it to you, right? Another way to do it is look at everyone's UID and see if it's odd or even, okay? Because the UIDs are approximately random, we can, with very high probability, suggest that roughly half the class will have an odd UID and roughly half the class will have an even UID, okay? And if that's the case, and your UID doesn't change, so if you come next week, you're going to get the same A or B as you did last week because your UID hasn't changed. So odds and evens will work. Does everyone follow that, right? Is this making sense? So when the student walks in the door of the lecture theater, I say, hey, if you're an odd, go to team A. If you're an even, go to team B. And hopefully everyone can see that we're going to have two teams, A and B, and they're going to be approximately even in size. Okay? Now, hopefully everyone understood that and it wasn't too hard to grasp. I'm going to go one step further and say, what if I want to run a basketball tournament and I actually want 16 teams? Okay, 16 teams. I'm going to divide the class of 400 or 500 into 16 teams. So how do I do that? Has anyone got a suggestion for how I solve that? So the first problem I had 2 teams, and now I'm saying 16 teams. Can anyone see a way to do that?
I got the suggestion from Joshua, so we use modular arithmetic, so mod 16.
Great suggestion.
Of the UIDs.
Yeah, so
Like that.
so Joshua has suggested that what we'll do is we take the UID as a person walks in the door and do modulo arithmetic or integer remainder in Java and say, okay, let's divide your UID by 16 and see what the remainder is, and then use that to decide which team you're in. And that's a perfect idea, okay? And it should, if the UIDs are approximately randomly distributed, you should find that all the teams are roughly the same size. Now, here's a question that's going to come up in C3, the module we do on Monday, I think, which is an intuition I want you all to grasp. How would I know if those teams were pretty even? Well, you just look at the teams, right? That's one sort of obvious answer. But if I used a histogram and I had and I drew the bars like in a bar graph, and the y-axis was team size, and then I had a bar for every team, what I want to see is those bars be very even, right? If some are really high and some are really low, then I know that I didn't do a very good job. That integer division by 16 wasn't working very well. On the other hand, if I found that all the teams were similar height in the bar graph, then I would know that that approach worked really well. Now, I want you all to remember what I just said then, okay? Think about the basketball teams. Think about looking at the UIDs, dividing the number by 16 and saying, what was your remainder? Now, everyone has to have a remainder between 0 and 15, right? Whatever your UID is, you divide by 16, the remainder is going to be some number between 0 and 15, okay? And you probably can't do 16 division in your head, but if you had a calculator or a computer, that's trivial, okay? So you do that, you get the remainder, and then it's going to give you a number between 0 and 15. That number will tell you which team you're in, okay? And that number is going to be the same as long as your UID doesn't change, and UIDs don't change, okay? All right, that's basically hash functions. You basically know it now. Here's the little formal bit. I'll just finish off very quickly. We're basically done with the lecture now, but I want to formalize what I just said. A hash function is a function that maps a key to a value within a prescribed range. So let's think about how that applies to what I just said. A function, and the function we started off with, we had basically the stuff that you were suggesting to me were functions, okay? And the function we finished with was take the UID, divide by 16, and the remainder is the value. So it's the value, so the key is the UID, so I take in the UID, that's the key, and the value is the remainder of the UID divided by 16. So you got a key, UID, value is the remainder of that UID divided by 16. Prescribed range means that I want the answer to this hash function to be a value, and I told you that I wanted 16 teams, okay? So that means that I want your hash function has to give a value between 0 and 15. Okay, 0 and 15 inclusive, right? It has to give it, that's the prescribed range. So it's no use if your hash function gives me the number 100. That's wrong, okay? That's incorrect. It needs to be within the prescribed range. That's a very important concept. So hopefully this statement sounds fairly formal, makes complete sense to you in the context of that example I gave you. A function, in this case it's integer remainder with 16, that maps a key, the key is the UID, and the value is that remainder, and it's within a prescribed range because you know for sure it's going to be between 0 and 15 inclusive. Deterministic, what that means is that the answer has to be the same every time, okay? So every time you apply that given key, the answer you get back has to be the same value. So if I do this multiple times with the same key, it always gives me back the same answer, which it will do if you do integer remainder, because the definition of remainder doesn't change, right? That's obviously going to happen the same every time. Choosing a good hash function. A good hash function for a given population will distribute evenly. And that's what I said before about the histogram. I said there's going to be a histogram. If you drew the size of the teams, then it would mean that all the teams were approximately the same size, maybe plus or minus one. Some were a little bit smaller and some were a little bit larger. But if some were huge and some were small, that would be a bad hash function, okay? So we want our hash function to give a nice, even histogram. We want to distribute amongst each of these things evenly, okay? And we talk about teams, but the language we normally use with hashes is buckets, okay? You talk about buckets. I'd say there's 16 buckets. In the example I gave, they were teams, okay? So we want all the buckets to have about the same in each one of them. And finally, a perfect hash is something which we did not do in that example. A perfect hash is where everyone gets a unique value. The value is unique for every single person, okay? So what's a perfect hash for the class? Okay, for a whole bunch of students? Well, one perfect hash, which is pretty silly, is just the UID itself, okay? Because every one of you has a unique UID, okay? So that's one way you could do it, okay? If you want to guarantee that everyone has a different number, but the problem with that is it's in a very big range then, isn't it? Because it's 7 digits. So it's, is it 7? Yeah, so it's 1 in 10 million, which is not really awesome. So that's a very big range. But it is a perfect hash, meaning that every student gets a unique number. Sometimes we want a perfect hash, sometimes we don't. With the basketball team, we obviously don't want a perfect hash of the basketball team because we want multiple people to be in the same bucket. That's the definition of the problem. In other cases, we do want a perfect hash, okay? So in a case where we do want a unique value for each key, that's what we call a perfect hash. And there are cases where that's what we want. But very often that's not what we want. Very often we'll have multiple keys get the same value. And the basketball team is an example of that. All right, that's that. And let's finally, I'll open up this quiz and then we're going to do the bio and then we're done. And I'm sorry I ran over time today. Let's do our bio. Ken Thompson. Ken Thompson is famous. He won the Turing Award, and what he's most famous for is one of the key developers of Unix. Okay, he helped develop Unix and also Multics, which is another operating system. And he did that with a guy called Dennis Ritchie, who's another amazing hero of computer science. One of the interesting things is that Ken Thompson developed a language called B, and B was the language he was going to use to help write Unix. But they ended up, Dennis Ritchie and Brian Kernighan ended up creating another language, which was called C, and they used C to build Unix instead of B. So B never went anywhere, but you can look up the language B, and it is actually the precursor of the C language. And the language C was designed and developed for the purposes of building Unix. So these two things are very closely related. Ken Thompson did other things such as help develop the idea of regular expressions and also the character encoding UTF-8. I'm going to leave it there. Have a great weekend, and I'll catch you on Monday. Don't forget the seminar that's on Tuesday. I think a lot of you will enjoy it. It's not compulsory at all, but I think you might find it really interesting. So have a great weekend, and